In this video, we are going to cover some equilibrium questions having to do with acids and bases. So let's get started. Find the pH of the following solution with acetic acid and some hydroiodic acid that is added to it. And we can solve that using an ice chart. So first, we know that we're having two acids being added to each other with different milliliter values, meaning the volume changes. So we can calculate the number of moles for our acetic acid and our hydroiodic acid. And then we can calculate the new molarity for acetic acid. You have 0.02 molar equals X over 0.1 liters. So you end up with 0.02. And then we can divide that by the new volume, which is 150 milliliters. So 0.15. And this equals 0.13 molar. Now the same thing for the hydroiodic acid. 0.1 molar equals X over 0.05 liters. And that's an equal 0.005 moles divided by your total liters now, which is 150 milliliters. And you get 0.033 molarity. Okay, so now we can solve for the ice chart. So let's draw our ice chart for the ionization of acetic acid in water. H3O plus our acetate ion. And our initial value for acetic acid is 0.13. And for the H3O plus, since the HI is a strong acid that has already been dissociated in water, we have our initial hydrogen concentration at 0.033 molar. Okay, so now this is going to be 0. So we can do our change, which is going to be minus X for the reactants and plus X for the products. So 0.13 minus X, 0.033 plus X, and X. So these are the values that are going to go into our equilibrium expression. So we can solve for that. 0.033 plus X times X over 0.13 minus X equals our Ka, which is 1.8 times 10 to the negative fifth. So this is what we're solving for, to solve for the pH. Now, our next question is, do we approximate? And it may not be as easy to tell in this case because our Ka is 10 to the negative fifth, but our concentrations are 10 to the negative third, or 10 to the negative second. Now, that's on the borderline, but you can do the approximation. So you can calculate it without the approximation versus with the approximation, and the numbers will be very close. So we can do the approximation here. And the rule is your Ka needs to be 10 to the third different than your concentrations. And in this case, or more, definitely more. So you should, if you have a 10 to the negative fifth difference or 10 to the seventh difference, that's really good. But in this case, it's exactly 10 to the third difference, or more. So it will be acceptable for this case. So we can remove the X's, then we can solve for X here, and we can obtain. And for X, you get 7.1 times 10 to the negative fifth. Okay, so now we're going to add that 7.1 times 10 to the negative fifth to our hydrogen ion concentration, or H3O plus, in order to get our total concentration after equilibrium is achieved, and we can use that to solve for our pH. So we're going to do the negative log of our 0.033 plus our 7.1 times 10 to the negative fifth. And as you can tell, most of the concentration of H3O plus will come from the strong acid. So the dissociation of the weak acid on top of that is not really going to contribute much to the pH. And our answer is 3.41 for the pH. Okay, moving forward. A 1 liter buffer of solution contains 0.1 molar acetic acid plus 0.1 molar of sodium acetate. So that's a buffer solution. The value of the Ka is that. Because the initial amounts of acid and conjugate base are equal, the pH of the buffer is equal to pKa of the log of the Ka, right? So pH equals pKa when the acid and conjugate base components of the buffer are in equal concentration or equal moles. And that's because of the Henderson-Hasselbalch equation. And it's asking us calculate the new pH after adding 0.01 moles of solid NaOH to the buffer. For comparison, calculate the pH of adding 0.01 moles of solid NaOH to 1 liter of pure water and ignore any small volume changes from adding the base. Okay, so let's do the water one first. So in pure water, you're adding 0.01 molar of NaOH. Okay, so this means we can directly find the concentration of OH in that water, of excess OH in that water, by doing 0.01 moles divided by 1 liter equals 0.01 molarity of the NaOH. And since it's a strong base, we can then do the negative log of 0.01, which is the concentration, which would be the POH, because we're using the concentration of the OH and doing the negative log of that to find the POH. And that would be equal to 2. Now we could do the pH of that solution would be 14 minus 2 equals 12. So even from adding that 0.01 moles of NaOH to pure water, it makes it extremely basic. So keep that in mind, that water, it doesn't really have that much of a buffer capacity. If it did, it would mitigate the pH change a lot better. So now let's compare that to a buffer containing acetate and acetic acid. So if we add the 0.01 moles of NaOH, what we can do is we can say that, all right, 0.01 moles of the acid, meaning acetic acid, is now going to be converted into conjugate base. So we don't even have to do an ice chart. We can just tell that 0.1 of, we'll call it HA as the acid, minus 0.01 of NaOH, because that is the amount that is going to be neutralized, now equals 0.09 of HA remaining. Then for the base, we have A minus, which we originally have 0.1 of that, and now we're adding the 0.01 of the acid, the HA, that was now converted or neutralized by the additional base to create more of the conjugate base. And that would be 0.11 of A minus. Now we can do the Henderson-Hasselbalch equation, and we can do the pH equals the pKa, which is 4.74 plus the log of the base concentration over the acid. And since they're both divided by 1 liter, the mole values are going to be the same as the concentration values. So it would be 0.11 divided by 0.09. And the answer for this is 4.94. So you can see how much the pH will change in a buffer compared to pure water when you're adding a strong either acid or base. The pH goes from 7.4 to 7.9 compared to going from 4.7 to 4.9 compared to going in pure water going from 7 to 12. So that's just proof that a buffer does a very good job of mitigating pH change. Okay, next one, titration of a strong acid. So in this case, when we're doing strong acid into strong base for titration rather than weak acid and weak base, all we have to do is figure out the acid or the base, whether they're in excess or not, and that will be used to determine the pH. So first, calculate the pH during the titration of the HCl with the 0.4 molar NaOH. First, what is the initial pH? All right, before any NaOH is added, we just do the concentration, we use the concentration of the acid, so negative log of 0.2. For the next one, we're being asked for the pH when you add 48.3 milliliters of NaOH. Now, first, we got to figure out the moles of both the acid and the base that are added. So the initial moles of the HCl is 0.2 times 0.1. So that's going to be 0.02 moles of HCl. Now the NaOH is 0.4 molar. So first we're adding 43.8 mils of that. So it'll be 0.4 times I'll do that over here, 0.4 times 0.0483, which equals 0.01932. Okay, so then from the original acid, we can subtract the base that is added because that is the amount that is going to be neutralized of the acid. And it's almost all of it. And this only gives us a remainder of 0.00068 moles of HCl. So that's the amount of remaining acid that is not neutralized. And in order to calculate the pH, we need to divide this by the new volume, which it's going to be 100 milliliters plus 48.3. So that's 0.1483. And our concentration is 0.00459. And we can do the negative log of this to get the pH, which is 2.33 or 2.34 if you want to round. Okay, next one. What is the pH after 50 milliliters of NaOH are added? So with 50 milliliters, it would be 0.4 molar of the NaOH times 0.05 liters of NaOH, which is 0.02. Now, we don't even have to do much math because we know we have 0.02 moles of the acid, and now we're being added 0.02 moles of the strong base. They would cancel out and neutralize completely, and your pH would be 7. And that's only true in a strong acid, strong base titration. If it was a weak acid, you'd have to use the Kb for that at the equivalence point. The next one is what is the pH after 63.1 mils of NaOH are added? So we do the same thing. We figure out how many moles that is. It'll be 0.4 molarity times 0.0631. Which equals 0.025. And we can subtract the 0.02 from the acid, because the base will neutralize all of the acid and there will be excess base. So that means you have an excess of 0.005, which then can be divided by your new volume to figure out the concentration. Our new volume is going to be 163.1, so 0.163, which is 0.031. Then we could do the negative log. I'll move the work up here. Negative log of 0.031 to obtain the POH, because we found the excess in hydroxide concentration. Which is 1.51. Then we could do 14 minus 1.51. For the pH to get 12.49. So with the excess base added, you're going to have a high pH, very basic, of 12.49. Okay, let's move on to the next one. You have 100 milliliters of 0.1 molar acetic acid are mixed with barium hydroxide. What determines the pH of the solution after the reaction? So we need to figure out how many moles are being added to see if it's completely neutralized or not neutralized completely yet. And we can solve for the pH as well. So the moles of this would be the moles of your acetate, your acetic acid, will be 0.1 times 0.1, which is going to be 0.01 moles. And they're mixed with 80 mils of 0.1 molar barium hydroxide, which is a strong base. So the moles of barium hydroxide will be 0.08. But you multiply that by 2, since there's 2 hydroxide moles per barium hydroxide, so 0.16. Now, after this solution, after the pH, well, to determine the pH, you know you have an excess of hydroxide ions. That means all of the acids going to be neutralized. And what will determine the pH of the solution after the reaction will be the amount of hydroxide, the amount of strong base that is there, and the difference. So you can do 0.16 minus 0.01, which would give you 0.15. And that would be the amount of moles divided by your total liters, 0.18 liters. And then you can determine the pH by doing the 14 minus the negative log of this. So this will equal the concentration, and then the concentration of hydroxide in excess. And you can do the negative log of that, which will give you the pOH. Then 14 minus that negative log value will give you the pH, which I'm not going to do here, but you can solve that on your own. Next one, you have 100 mils of the same thing, acetic acid, but at double the concentration. So that means you're going to have double the moles as the first one, so 0.02 moles. And you're being mixed with 50 mils of 0.1 molar NaOH, which the amount of moles of that is going to be 0.05 moles. Oh, sorry, 0.05 moles. So then what determines the pH of the solution after the reaction? So in this case, you have less base moles that are added to the acid. So not all of it's going to be neutralized, but only a small portion of it. So we're going to subtract the base moles to figure out exactly how much that is. So you're going to have 0.015 moles of acid left, and then you're going to have 0.005 moles of your conjugate base. We'll call that A minus and HA. HA, not HA minus. Okay, so from this, we can now use Henderson-Hasselbalch. And we're not going to do it up over here, but the pH will equal the pKa of acetic acid, which we saw in previous problems, plus the log of the base concentration, meaning the conjugate base. So it'll be 0.005 divided by the liters, which is 0.15, over the moles of the weak acid that are remaining, that are not neutralized, so 0.015 divided by your total liters, so because it's concentration, and then you solve for this to obtain the pH. So the answer to this is the Henderson-Hasselbalch or buffer equation will be used to calculate the pH after the reaction. All right, for this solubility question, we have calculate the solubility of copper 2 iodate in 0.43 molar copper 2 nitrate, and the KSP is 7.4 times 10 to the negative 8th. Now this KSP is for copper 2 iodate because it is a weak electrolyte, and we know that because all nitrates are strongly soluble. So the copper 2 nitrate is going to be your strong electrolyte. So what we can do here is we can say we're calculating S for solubility. Now we can kind of write a dissociation of copper 2 iodate. So copper 2 iodate is CuIO3 parenthesis 2, and that will be copper 2 plus IO3 or 2 IO3 minus. So we can say that our solubility of it, which we know will equal our KSP, the molarities will be S, which would be for our copper, plus or times 2S squared, because our iodate is going to have its solubility as well, and S is going to be your total solubility, and this is going to be equaling our KSP, which is KSP, which equals 7.4 times 10 to the negative 8th. Now, solubility, originally we can calculate the solubility by solving for S. But since we're adding another ion into the mix and observing the common ion effect, we can solve for S using this concentration. So 0.43 molar copper 2 nitrate is actually 0.43 molar of copper, and doesn't matter, but 0.86 molar of nitrate. And that's not really going to affect our equation at all. But this molar of this additional concentration of copper has to be added to S over here. So it'll be S plus 0.43. And you can see adding this 0.43 is going to decrease S. That's the goal here of the common ion effect, is because what we're doing is we have a baseline solubility for copper 2 iodate. Since we're adding more copper, you can imagine that the solubility or the equilibrium will shift more towards the left, as Le Chatelier's principle suggests, which that dictates the common ion effect as well. So that's what we're doing here. We're adding more of this to move the equilibrium into the precipitation direction. And this is going to equal our KSP. And then we can solve for S, which S is going to be equal around 3 times 10 to the negative 4th molarity. Moving on to the next one. For the reaction given here, what is Q when 2 milliliters of 0.023 molar lead nitrate is added to that much of sodium chloride? All right, now sodium chloride is our strong electrolyte, and also lead nitrate is also strong. But for this equation, what's going on? So we got to write an ice chart for the dissociation of lead chloride, which we know is a weak electrolyte. Now the KSP for lead chloride is 1.6 times 10 to the negative 5th. And that we can use that later on. But first, we have, what are we being given in terms of molarities of lead and for chloride? So what is Q when 2 milliliters of 0.023 lead nitrate? So lead nitrate, in this case, it's going to be, we assume it's lead 2 nitrate. So it would be PbNO3 2. And we can say that 0.023 equals X over 0.002 liters. And this is going to be equal 4.6 times 10 to the negative 5th moles and of lead. And then we have the amount of sodium chloride, which is 0.025 times 0.016, which is going to be 4 times 10 to the negative 4th moles of NaCl. So now we can find the new concentrations and divide this by the new liters, which is 18 milliliters, so 0.018, and same thing with the NaCl. So our new concentration is 4.6 times 10 to the negative 5th divided by 0.018, which is 2.56 times 10 to the negative 3rd molar. And then for here, we have 2.22 times 10 to the negative 2 molar. Okay. So what we're doing here is we're calculating Q. Now Q for solubility is going to be equal to 2 times the molar solubility of Cl squared times Pb2 plus. Now we can calculate that. So it would be 2S plus the Cl concentration that we just added, which is 2.2 times 10 to the negative 2, times our Pb2 plus, which is going to be S plus the lead that we just added. So that's going to be 2.56 times 10 to the negative 3rd. And once we solve for S, and the way we can solve for S is by using our KSP, 1.6 times 10 to the negative fifth equals PB times 2, equals S times 2S squared. And we can solve for S, and then we can put this S into this equation and solve for Q. And I'm not going to do that part here, but the answer is 9.9 times 10 to the negative fourth. Okay, that's it for this video. If you have any questions, you can comment below, and please like and subscribe.